Now Faraday, what do we know about Faraday? Faraday, what? Liked to make life easier on himself by imagining fake lines of force. So, what did he do with magnetism? Made fake lines of force. And so he imagined that if you had magnetic fields, they look something like this. And then these are the flux lines of magnetic force. And that your things are flying through this flux line and they're getting turned around the flux lines and all that stuff. He then noticed the following interesting observation. What did magnetic fields like to do, sir? No. They make things go in a circle oftentimes. What is it magnetic fields do? They what? They attract the metals. What is the principal value of a magnetic field? What does it want to do more than anything else in the universe? I'm going to go home now. What does an inductor do?
Resist change.
Resists change. The reason why a magnet works is you take two magnets, pull them apart. What happens? They go back together again, right? Generally speaking, magnetic fields don't spontaneously cause change. It's a good thing because we got one around the whole entire planet. So magnetic fields resist change. And so our boy Faraday noticed the following. If you take a wire and you have a loop of wire, which has a bunch of electrons in it, nothing going on, and you just stick it in a magnetic field, nothing happens. Absolutely nothing. Just sits in there happily doing nothing. But if I were to in some way change the wire, make it grow, get bigger, it would suddenly enclose more magnetic field. If it did that, the wire would do what in response? It would want to go shrinking back, but wires can't do that. So what instead would happen? What can respond to a magnetic field? Charged particles. Specifically, what charged particles? Electrons start moving, and the reason why they start moving is to stop the nonsense. You're making more magnetic field inside here. I'm going to do what instead? I'm going to stop it by making a magnetic field the other way by running current the opposite direction to maintain equilibrium. So what happens is as you start to make the wire bigger, the loop bigger, you're creating more coming out in the board, right? So the wire would run current so that would create magnetic field the opposite direction. To stop it. And that current, by the way, would be going which way around my wire? If I try to go this way, that would make it worse. So it's going to go this way to make it better. So your current would end up going this way around the field as you made it bigger. By the way, if you shrink it, the current would then go the other way, would it not? And this creates voltage. Right? Because there's resistance in the wire and I'm drawing current, aren't I? So what am I creating? I'm creating voltage. So if you want a power supply, you monkey with wires and magnetic fields, which is essentially what every every generator does. You monkey with a wire. You create situations where you're changing the amount of the magnetic flux lines. That's going to create voltage. And so basically he wrote the simple statement like this. And what was interesting about this is he didn't really care what was inside there. He said this has to be true. If I change the flux, the number of flux lines inside of my circle, my loop, then I'm going to create voltage. Period. And then he proceeded to define these flux lines in terms that would make the equation work. Agreed? Understand, sort of? Now, I want you to know something. If there's no loop, does this work? It can't run current to nowhere. So you have to have a loop. That loop has to enclose flux lines. You can do it. So how are we going to define the flux lines? Well, the flux lines are what? What is a flux line? In electric field, it was a measurement of the electric field. So in Magnetism is going to be the magnetic field. It's going to be the magnetic field times the area. You guys remember before how we had to have it going the right way because if you have more an angle, you get less lines? We're going to do the same thing here. We're going to attach a cosine theta onto the end of this. So if you want to make voltage, you simply have to vary one of these with respect to time. So there are three ways to make voltage. You can have A cosine theta dV dt, change the magnetic field. You can B let me do this so it's consistent. B cosine theta dA dt. Change the area. Make the loop bigger or smaller. You can change the angle at which it's operating. Because remember, we're trying to conserve the number of flux lines going through my loop. And if I change the angle of the wire, I change the number of flux lines. If I turn it a little bit sideways like this, I got less flux lines going through there, don't I? The magnetic field's going this way. Now, this is the one you use the most in real life. The easiest way to make a generator is to take some stupid wires, create some magnets, get some magnets, stick them on the outside. Take a coil of wire. On the other end of the coil wire, you attach it to something paddle wheelie. Turns the wires inside. The wires turning inside. Change the angle. The wires, in angry response, create a magnetic field to stop that nonsense by running current. You take the current off that coil, you run it to somebody's house, they turn on their lights, you run it back to the power plant. Problem with that system, by the way, is what? Once the thing flips over, which way is the current going to go? The other way, right? Because it's resist that change, which means it's going to run electrons backwards through your house, which is AC current. That's what AC current is. Because the thing flips over, it's going to run current the other way, back and forth. And that's why we do AC current, because it's the easiest way to do it. On the AP test, this is hard to calculate. These are weird things, like what angle am I at? How fast my angle changing? Oh, the rates problem. Isn't that fun? So which one you're more likely to see on the AP test? The other two, which is nice, because it's easy to do. Easier to do. Okay? At least to look at, intellectually speaking. All right, so let's flip this over. Let's try problem number 1 on the back. Yes, sir?
How do you change AC to DC?
That means a loop in a plane, right?
What? No. Yes.
And then it says a wire is consistent of a single turn cross-sectional 100 centimeters squared or something useless like that. Boy, I hate that unit. That would be a 10 by 10 centimeters if it was a square. Since it doesn't matter what shape it is, I'm going to go ahead and make it a square. And so that would be a 10 by 10, which would be what would be its meters? Because we needed meters. 0.01 meters squared would be my area. Agreed? Okay. So I just read the first part. We're going to keep going. It says in a perpendicular magnetic field, perpendicular, that's nice. Perpendicular.
It's zero.
No, well, you're thinking zero, but wait a minute. Which way does the area vector work? Out of the inclined plane. So it's strongest, and you should think about it this way. It's strongest when the magnetic field is passing straight through the loop, right? It's perpendicular. No loops, no flux lines are going through the loop anymore, right? So this is perpendicular to the This is perpendicular to the magnetic field. The loop is perpendicular, which means it's going straight through it, which means strongest, which means the cosine is actually cosine of 0. Yeah. But again, just think about it in terms of it's strongest when they're all traveling through. You want most lines going through creates the most flux, right? And so is this the situation where you have the most? Yes, because it's perpendicular to the magnetic field. It's mostly going through there. That's the most situation. If you tilt it even a little bit, you lose magnetic flux lines. Next, man, I need you with me. You can't take a vacation now.
I'm here.
All right. So perpendicular is nice, and then we keep going. It says the magnitude is changing. So the magnetic field is going from 0.5 to 2.5. It's doing that in 1.5 seconds. Is that changing? That's changing. And then it says, what is the resulting induced current if the coil has a resistance of 4 ohms? So far with me? So let's try this out. We go, first of all, we go V equals IR. Love it. Don't know the voltage, don't know the current. We know the resistance is 4. That's exciting. Can't solve that problem. We need voltage. Why is there voltage at all? Because somebody's changing the magnetic field, right? So I go d dt of BA cosine theta. I want you to write it that way on the test. That is not the way they want you to write it. I don't care. Write it that way on the test because you won't make a mistake. Now I go to the list. Is this one changing? Yes. Is this one changing? No. Is this one changing? No, I'm not changing the angle at all, but I'm tilting it. That's going to give my voltage. Therefore, my voltage is going to be equal to A. That's not changing. I pull it out. Cosine theta, which is cosine of 0 degrees, or 1, times dB dt. What is the rate at which my magnetic field is changing? Mr. Bernard. Every
Per 1.5 seconds.
Love it. Exactly what you should have said right there. 2 divided by 1.5. Sometimes they can give you a formula, in which case you take the derivative of the formula. Sometimes they just tell you it's changing this much at this time. Just divide it out. And I get my voltage is equal to I get 0.01333, is that right? And then I just do B equals IR, 0.01333 equals I times 4. I get that my current is 3.33 times 10 to the negative third amps. Does that make sense? So what's the strategy? The strategy is, look, you can't make voltage unless one of these 3 things change. You can use this formula to find what the voltage is. Once you have the voltage, you can do all the things you know what to do with voltage. Every time.
Never mind.
Okay,
It's like, nope.
good? Does that make sense? Figure out which one's changing, take the derivative of it. If it's a linear thing, it's a piece of cake, take the derivative, you just divide out, find the rate correctly. Yes?
Kind of off topic, but it looks like you wrote bacon.
Yeah, that's what I was thinking.
Bacon, all right, bacon, that's where you remember it. It's not on your formula sheet that way, but bacon. How about Bacos theta? Bacos theta.
That's not as fun.
Bacos theta. It's not on your formula sheet, so you're responsible for remembering what it is. Bacos theta will work.
Bacon.
Bacos theta. All right, everybody try number 2.
It's like the fake bacon that.
Oh wait, Brandon, what is coils going to do to me?
Yeah.
Coils. How's that going to affect things? Multiple that coils now.
Gonna make it multiplied by it.
Multiply by that at the end. You get your voltage times however many coils you have.
But then doesn't it